Next is reactions of alkenes. Reactions of alkenes. The reaction is known as electrophilic addition reaction. What is that? Electrophilic addition reaction. Electrophilic addition reactions of alkene. First one is electrophilic addition reaction, and examples of electrophilic addition reaction. First one is addition of halogens. Addition of halogens. We get dihalides. Do we get dihalides? That means we get vicinal dihalides. Look at here. When an alkene CH2 double bond CH2 react with halogens like Br2, you can see that this bond is breaking, or you can write it as a CH2 double bond CH2 plus Br2 can be written as a Br. Okay, you can see that this bond is breaking and this bond is breaking. One Br is coming to this carbon and the other Br is coming to this carbon. So what we get? We get CH2Br single bond CH2Br. We get vicinal dihalides. You can see that the halogen atoms are in the adjacent carbon atoms, and this is what is called addition of halogens. Okay, example CH2 double bond CH2 plus Br2. You can see that this bond, one of the double bonds, okay, the pi bond is breaking, and here Br bond is breaking. One Br is coming to this carbon and the other Br is going to this carbon. So you get CH2Br. Look at the mechanism of the reaction. This is not the mechanism. Let us go through the mechanism of the reaction. Mechanism. Okay, CH2 double bond CH2 plus Br2 means Br, and you know that this Br bond is partially, it is getting a slight polarization. That means this is a slightly polar in nature. That means one Br is delta positive and the other Br is delta negative. Okay, delta negative. Now you can see that this can act as a electrophile. This is acting as a electrophile because it is positively charged. This is a electrophile, and you can see that this double bond, one bond is pi bond. This pi bond breaks from one carbon. Okay, suppose it is breaking from this carbon, and you will abstract this electrophile only. This Br plus is subtracting, and what will happen that time? This bond is shifting to this Br. Okay, and what we get? You get. Look at it here. When the pi bond, this pi bond breaks heterolytically. That means, look at it here. The pi bond breaks from this carbon, and it is abstracting this Br, and which will result in the formation of a cyclic halonium ion. So you can see that this Br is coming to this pi electron cloud, and which will result in the formation of a cyclic halonium ion. Br here it is CH2, and it is getting a full positive charge. Once again I repeat, this Br is abstracting into this pi system. Okay, this Br is abstracting into the alkene. This Br is coming into the alkene, and which will result in the formation of a cyclic halonium ion. This is known as a halonium ion, and plus what will happen? This bond is shifting to this Br, so this Br will become completely negatively charged, Br minus. Okay, so this is the first step, formation of a halonium ion. This is an intermediate. Okay, now once again I repeat, this Br plus, that means this can act as electrophile, positively charged. This will be abstracted into the pi system, or this Br plus is abstracting into the alkene, which will result in the formation of a cyclic halonium ion, and at the same time this bond is migrating this Br, so it is changing into Br minus. Now this Br minus is acting as a nucleophile. This Br minus is acting as a nucleophile. So this is step 1. Step 1, what is that? A formation of halonium ion. And now in step 2, what is happening in the step 2? Look at it here, our halonium ion, CH2, and Br, here Br having a positive charge because the Br is making 2 bonds. Okay, the halogen is making 2 bonds. That means definitely it will have a positive charge. Halogen can make only 1 bond. The second bond, that means utilizing its lone pair electron, so it is getting a full positive charge. And you can see that now in the second step, our nucleophile, that means the Br minus, this Br minus nucleophile attacks the halonium ion from the opposite side of the bulky portion. So this Br minus is acting as a nucleophile. That nucleophile will attack the halonium ion. This Br minus is attacking the halonium ion from the opposite side of the bulky portion. This is the bulky portion. So from the top it will have steric effect. Therefore, the Br minus is attacking from the opposite side of the bulky portion. That time what will happen? This bond will break, and it will this electron will be shifted to Br. So what we get? We get CH2. Now this bond is breaking. Then here it will become a this Br will become free, and CH2 Br, and here you are getting CH2 Br. You get vicinal dihalide, you get dihalide. Okay, this is the mechanism of addition of halogen. That means in the first step, a halonium ion is forming. The electrophile Br plus is abstracting into the alkane, which will result in the formation of a cyclic halonium ion. In the second step, the halonium ion will be attacked by the Br minus, by the nucleophile, negatively charged species. This is known as nucleophile. The nucleophile will attack the halonium ion from the opposite side of the bulky portion. Will result in the breaking of the opening of the cyclic system, and will give dihalide. Okay, when it attack from the back side, what will happen? The ring will open, and we get vicinal dihalide. This is the mechanism of electrophilic addition of halogens. Okay. Now we can take one more example for addition of halogen. Look at it here. If you take CH3, CH, double bond CH, single bond CH3, but2ene is reacting with Br2. What you will get? What is the mechanism? Okay, you look at it here. The mechanism: CH3, CH, double bond CH, single bond CH3 plus Br2 can be written as Br. One is a delta positive and the other one is a delta negative. So this pi electron system, this is pi bond, will abstract this one. So what will form? We get, and at the same time this bond will be shifted to here. So we get CH3, CH, single bond CH, single bond CH3, and the Br will be like this. It will form a halonium ion. Okay, a halonium ion, and what will form? Plus Br minus. This is the first step. Okay, in the second step, what will happen? In the second step, this Br minus will attack from the back side. Then this ring will open. Okay, so what we get? We get CH3, CH. Here it will become Br, and here it is a CH, Br, single bond CH3. Clear? Okay, this is the mechanism of addition of halogens. Next, second addition of hydrogen halides. Second reaction. First one, addition of halogens. Second one is addition of hydrogen halide. Addition of hydrogen halides. Okay. Look at here. Addition of hydrogen halide. When an alkene CH2 double bond CH2 is react with hydrogen halide. Example is HCl. what you will get? You can see that CH2 double bond CH2 plus HCl. Okay, like in the addition of halogens, this bond will break. HCl. Okay, hydrogen will go to one carbon and the halogen will go to the other carbon. So what we get? We get CH2 and hydrogen is coming to this carbon, means what will have, it will become CH3. And here you can see that this Cl is coming to this carbon, so what will get? CH2 Cl. So what will form? We get alkyl halides. Alkyl halide. Addition of hydrogen halide. What we will get? We get alkyl halides. Okay. CH2 double bond CH2 plus HCl. Okay. Suppose this hydrogen is coming to this carbon. Then what will I get? CH3 CH2Cl. You get the same product. You get the same product because this is a symmetrical alkene. Symmetrical alkene. Symmetrical alkene means look at here, this double bond, this side is CH2, this side also CH2. So in the case of symmetrical alkene, you get the same product. If hydrogen is coming to this carbon or the hydrogen is coming to this carbon, makes no difference. You get CH3 CH2 Cl. CH3 CH2 Cl. Now the mechanism of the reaction. Look at the mechanism. CH2 double bond CH2 plus HCl. Okay, and you know that hydrogen and halogen bond is a polar bond. Of course, hydrogen is slightly positively charged, delta positive, and chlorine is delta negative. Now look at this mechanism. Now you can see that as in the case of our addition of halogen, you can see that this bond, this bond, okay, suppose the bond breaks from this carbon, and it is taking, so the bond breaks from this carbon and you will abstract this H plus and this bond is shifting. Okay, here there is no halonium ion formation. Okay, it is not like that. Look at here what is happening. Look at here, since this bond breaks from this carbon, CH will become getting a positive charge because this bond is breaking from this carbon, so the carbon is getting a positive charge, and this CH2 will become CH3. That means we get a carbocation. This is the first step. Step one. Formation of carbocation. Formation of carbocation. What do you mean by carbocation? Formation of carbocation. Carbocation is a positively charged carbon. Okay, this is the first step. In the addition of halogen, the first step was formation of halonium ion. Here it is a formation of carbocation. And in the second step, step two. Now plus what will form? Plus Cl minus, this Cl minus, Cl minus. Now in the second step, attack of the nucleophile. This is acting as a nucleophile, negatively charged species. Nucleophile. Attack of the nucleophile on the carbocation. So what is that? We have CH2, CH3. Here it is a positive charge. Now our nucleophile. What is our nucleophile? This Cl minus. This Cl minus will attack on this. This Cl minus will attack on this positively charged carbon. And what we get? We get. You can write first CH3, CH2, Cl. Attack of the nucleophile on the carbocation. This is positively charged carbon. On that carbon, what will happen? The Cl minus will attack and we get CH3, CH2, Cl. This is the mechanism of addition of hydrogen halide. So in the first step, what is happening? In the first step, what is the formation of a carbocation? The pi bond breaks and it will abstract this H plus. So this carbon will get a positive charge and this CH2, and it is getting one more hydrogen, so it will become a CH3, and this is a carbocation. And in the second step, the nucleophile, here the nucleophile is formed. That nucleophile will attack on the carbocation, will give alkyl halide. Okay, another example. or here we discuss let us discuss some more examples. Before that, we come to Markovnikov's rule. Markovnikov's rule. This also you have studied. Markovnikov's rule. Okay. What do you mean by Markovnikov's rule? When an unsymmetrical alkene or when an unsymmetrical reagent is added to an unsymmetrical alkene, the positive part of the reagent will go to that double bonded carbon which already having the highest number of hydrogen atoms. So according to Markovnikov's rule, when an unsymmetrical reagent is added to an unsymmetrical alkene, the positive part of the reagent will go to that double bonded carbon which already having the greatest number of hydrogen atoms, When an unsymmetrical reagent, what do you mean by unsymmetrical reagent? See, in the first reaction was addition of halogen. Addition of halogen means Cl2, or example is addition of halogen is Cl2, that means Cl. This is a symmetrical reagent. This side also Cl, this side also Cl. This is a symmetrical reagent. So this is not unsymmetrical. So we need, when an unsymmetrical reagent, suppose addition of hydrogen halide, HCl. This is an unsymmetrical reagent because here it is hydrogen and here it is chlorine. So this type of reagent, unsymmetrical reagent, when an unsymmetrical reagent is added to an unsymmetrical alkene. What do you mean by unsymmetrical alkene? Suppose we take ethene. This alkene is not unsymmetrical. This is a symmetrical alkene because see, look at here, left side CH2, right side also CH2. This is a symmetrical alkene. So we need unsymmetrical reagent. Of course, this is unsymmetrical reagent and we need unsymmetrical alkene. So look at here, unsymmetrical alkene. Suppose we take CH3, CH double bond CH2. What is this one? This one is propene. This is propene. Okay. Now look at here. Here, this is unsymmetrical alkene. What do you mean by unsymmetrical alkene? Look at the double bond. Okay. Right side CH2, left side CH3. So this is not symmetrical, different only. So in this case, okay, now we are taking HCl plus HCl. So now our condition is clear. This is unsymmetrical reagent and this is unsymmetrical alkane. So when an unsymmetrical reagent is added to unsymmetrical alkene, the positive part of the reagent in HCl, which is the positive part, H plus and Cl minus, the positive part of the reagent will go to that double bonded carbon, which is our double bonded carbon, this carbon and this carbon. This is the double bonded carbon, will go to that double bonded carbon which already having the greatest number of hydrogen atom. In this double bonded carbon, which carbon is having the highest number of hydrogen atom? This carbon has 2 hydrogen atom and this carbon has only 1 hydrogen atom. Therefore, according to Markovnikov's rule, the positive part of the reagent will go to that double bonded carbon which already having the highest number of hydrogen atom. That means this H plus will go to this carbon. That means the bond will break, HCl bond will break and this H will go to this carbon. H will come to this carbon and Cl will come to this carbon. So here you are getting what is that CH3 CH Cl, and here it is CH3. This is the major product. What is this one? Major product. Of course, you will have a slight amount of minor product. In that case, what will happen? The hydrogen will come to this carbon and Cl will come to this carbon. That means CH3 CH2 CH2 Cl. Actually, this is a very minor product. Okay, this is the major product. Okay, so look at here. When an unsymmetrical reagent, one is H and Cl minus, is added to unsymmetrical alkene, the positive part of the reagent will go to that double bonded carbon which already having the highest number of hydrogen atom. So this H plus will come to this carbon. That means it will become CH3 and Cl will come to this carbon. You get this is the major product. Okay. So this is what is called the Marconi-Coffs rule. One more example for Marconi-Coffs rule. Let us take CH3 CH3 CH double bond CH2 plus HCl. Now in this case, again, what is that? You can see that this is positive and this one is negative. This is unsymmetrical alkene. According to Marconi-Coffs rule, what will happen? This is the double bonded carbon. This carbon is having 2 hydrogen atoms. So this is the carbon with the greatest number of hydrogen atoms. Therefore, the positive part of the reagent will come to this carbon. The bond breaks and the Cl will come to this carbon. Okay. So what we get? CH3 CH. Here it is CH3. Sorry. We need only C. Sorry. Here it is C. Okay, that means here the hydrogen, this carbon is having the highest number of hydrogen. Therefore, the positive part will come to this carbon, so it will become. You can see that the Cl will go to this carbon, Cl, and you can see that here it is CH3. Okay, this is the major product. Okay, this is the major product, and that is it. In the previous case we told that there is a possibility of forming minor product also. What do you mean by minor product? Minor product means what will happen? The H can come to this carbon. So CH3 CH3, here it will become H, and here it will become CH2Cl. But in this case you can see that there is no possibility of forming this minor product. No possibility of forming the minor product. You can see that what is the driving force? Why this reaction is happening like this? Why the positive part is always going to that double bonded carbon which is having the highest number of hydrogen atom? What is the reason for that? Look at here. We know that the mechanism of the reaction. What is that? CH3 CH3 double bond CH2 plus HCl. What is the first step? Step 1 is the formation of carbocation. That means you can see that there is 2 possibilities. The bond can break. This bond can break from this carbon, and so if it is breaking from this carbon, okay, this is the first possibility. Okay, then what will form? We get you can look at it here, CH3. Here it is CH3, and since the bond is breaking from this carbon is getting a positive charge and a single bond CH3, and you can see that this is a tertiary carbocation. What type of carbocation? Tertiary carbocation. This tertiary carbocation is highly stable. Okay, highly stable. Another possibility, suppose this bond breaks from this carbon. Okay, look at here, CH3 double bond CH2 plus HCl. Now suppose the bond breaks from, in the first case the bond is breaking from this carbon, therefore this carbon is getting a positive charge. Now in the second case the bond breaks from this carbon, the bond is breaking from this carbon and it is subtracting, okay, and is subtracting. So what we will get? We get since the bond is breaking from this carbon, this carbon is getting a positive charge. In that case what we get? CH3, and here it is H, and what is it? Here it is CH2 plus, correct, and plus Cl minus, here also plus Cl minus. Now in this case this is a primary carbocation, this is highly unstable. Primary carbocation is highly unstable, therefore no possibility of forming this carbocation, that is the reason only this carbocation will be formed, and in the second step what will happen? Our Cl minus will attack on this carbon, you get this product, and in this case this carbocation will not be formed because this carbocation is highly unstable, therefore no possibility of forming this product. Clear? Okay. And one more point. Peroxide effect. Peroxide effect. Peroxide effect or Karash effect. Karash effect. What do you mean by Karash effect? In the presence of a peroxide, example benzoyl peroxide or sodium peroxide, the above reaction will follow anti-Markovnikov's rule. Anti-Markovnikov's rule. That means CH3, CH, double bond CH2 plus HBr. Usually this reaction will be given by hydrogen bromide. If this is the reaction in presence of a peroxide, example benzoyl peroxide. Okay, in the presence of benzoyl peroxide, if there is no benzoyl peroxide, what is the product? According to Markovnikov's rule, the positive part, this is the positive part and this one is the negative part. The positive part will go to this carbon because this carbon is having the highest number of hydrogen atom. If there is no peroxide, but in the presence of peroxide, what is the product? According to this reaction will follow anti-Markovnikov's rule. That means the positive part will go to this carbon. So in the presence of benzoyl peroxide, what is the product? CH3. This hydrogen atom will come to this CH2 and CH2Br. This is the product. Okay, this is what is called peroxide effect or Karash effect. That means in the presence of a peroxide effect, the addition of hydrogen halide into an unsymmetrical alkene will follow anti-Markovnikov's rule. Okay, or we get anti-Markovnikov's product. Okay, thank you. We continue in the next class.